In the early days of January 2026, a team of astronomers at the Massachusetts Institute of Technology gathered around a screen in a small office and looked at a number that should not have been there. The number was 14.44. To anyone outside the field, it was just a decimal. To them, it was a wound in the standard model of cosmology. It meant that the galaxy they were looking at had emitted its light over 13.5 billion years ago. It meant that this galaxy existed when the universe was only 280 million years old, less than 2% of its current age. And it meant that this galaxy, sitting at the very edge of what light has ever been able to deliver to a human instrument, was brighter, more compact, more chemically rich, and more mature than every model said it had any right to be. The lead researcher, Rohan Naidu, would later describe it with a single line that has stayed with cosmologists ever since. With Webb, we are able to see farther than humans ever have before, and it looks nothing like what we predicted. Tonight, we are going to walk to the edge of the universe. We are going to follow the light from the most distant object ever confirmed by human science, back through 13.5 billion years of expanding space to a moment when the cosmos was still being born. We are going to see what the James Webb Space Telescope, an instrument that took 25 years to build and $10 billion to launch, has actually found there. And what we are going to discover is that the universe in its infancy was doing things that our best theories cannot account for. Galaxies that should have been faint smears of primordial gas are instead blazing structures. Stars that should not have had time to form are already burning. Heavy elements that required generations of stellar death are already present. The universe at 280 million years old looks less like a nursery and more like a place that has been running for billions of years longer than the clock allows. And every new observation is making the problem worse. If you enjoy these nighttime journeys into the deepest questions science can ask, take a moment to like this video and subscribe to Hidden Beyond Stars. It helps us reach more curious minds, and it lets us keep building these long-form explorations for you. Now let us begin. There is a quiet violence in the way the James Webb Space Telescope sees. It does not capture light the way our eyes do. It captures the infrared, the long wavelengths that have been stretched across the expanding universe for billions of years, until they slip beyond the red end of the visible spectrum entirely. When you look up at the night sky with your naked eye, you are seeing photons that left their sources a few hundred or a few thousand years ago. The light from Andromeda left 2.5 million years ago, well before any human civilization existed. The light from the farthest galaxies the Hubble telescope could resolve left about 13 billion years ago. But there is light that even Hubble could not see. Light so old, so stretched, so weakened by the expansion of space itself that it has shifted entirely out of the visible band. That light is what Webb was built to catch. The telescope was launched on Christmas Day, 2021. It rode an Ariane V rocket into space, separated from its booster, and began the most complex deployment in the history of spaceflight. Over the next month, it unfolded a tennis court-sized sunshield made of 5 layers of aluminum-coated plastic, each layer thinner than a human hair. It deployed a primary mirror made of 18 hexagonal segments coated in pure gold, 6.5 meters across when fully assembled. It traveled 1.5 million kilometers from Earth to the second Lagrange point, a gravitational sweet spot where it now orbits the Sun in lockstep with our planet, permanently shaded from the light and heat of the Sun, the Earth, and the Moon. There, in the cold and the dark, with its instruments cooled to just a few degrees above absolute zero, it began to look. It was designed for one purpose above all others: to see the first galaxies. To find the dim, struggling, half-formed collections of gas and the earliest stars that emerged from the cosmic dark ages, a few 100 million years after the Big Bang. The expectation was specific. According to the standard model of cosmology, the model that had survived every test for a quarter of a century, the first galaxies should have been small, faint, and chaotic. They should have been little more than gravitational pockets of hydrogen and helium gas, beginning to ignite their first generation of stars. They should have been almost invisible, requiring hundreds of hours of observation to detect at all. And once detected, they should have looked simple, disorganized, primitive. Webb was supposed to confirm the long, slow, gradual story of how galaxies built themselves over billions of years. Webb was supposed to deliver the final triumph of the lambda cold dark matter model, the standard picture in which structure forms slowly, conservatively, and predictably through the patient work of gravity. That is not what happened. Within months of beginning science operations, Webb started returning images that made researchers reread the data, then check their instruments, then check their math. The galaxies in the deep field images were not faint smears. They were bright. They were not chaotic. They were structured. Many of them were already shaped into disks. Some had the unmistakable signatures of central bulges, of spiral arms, of stellar populations that should have required generations to form. And the most distant of them, the ones sitting at redshifts above 10, were the most surprising of all. By the end of 2022, Webb had identified more than 100 galaxy candidates at redshifts greater than 10. By the standards of pre-launch predictions, that number should have been close to 0. The pre-launch models had predicted that bright galaxies at those distances would be vanishingly rare, perhaps a handful across the entire sky. Webb was finding them in every deep field it pointed at. The number density of bright galaxies in the era, from 400 million to 600 million years after the Big Bang, turned out to be more than 100 times what the consensus models had said it should be. Not slightly more, not double, not 10 times. 100 times. The first instinct in any scientific community when faced with an impossible result is to suspect the measurement. Perhaps the redshift estimates were wrong. Perhaps the galaxies were not as distant as they appeared. Perhaps something in the calibration of the instrument was producing artifacts that mimicked the signatures of early galaxies. So the astronomers did what astronomers always do. They went back and they checked. They obtained spectra. They confirmed redshifts. They cross-referenced their findings against independent observations from other instruments. And one by one, the impossible galaxies refused to disappear. They were real. They were where Webb said they were. And then in January of 2026, the team led by Rohan Naidu announced the most extreme example yet. They called it MOMZ14. The MOM stood for Mirage or Miracle, the name of the spectroscopic survey designed specifically to confirm the most distant candidates that had been identified in photometric surveys. The Z14 was the redshift, 14.44 to be precise, confirmed through detailed spectroscopic analysis with the near-infrared spectrograph aboard Webb. That number, 14.44, placed MOMZ14 firmly as the most distant galaxy ever directly confirmed by spectroscopy. The light that Webb had captured from this object had been traveling for 13.5 billion years. When that light had left the galaxy, the universe was only 280 million years old. And the galaxy was already doing things that should have been impossible. Let us walk through what makes MOMZ14 such a problem. To understand the strangeness, you have to first understand what the universe is supposed to look like at 280 million years old. In the standard picture, the universe emerges from the Big Bang as a hot, dense, almost perfectly uniform plasma of hydrogen and helium nuclei, free electrons and photons. The plasma is so dense that light cannot travel through it. Photons are constantly scattered off free electrons. The universe is opaque. About 380,000 years after the Big Bang, the universe cools enough for electrons to bind with nuclei. Neutral atoms form. The plasma becomes a gas. Light is released. The photons that were freed at that moment are what we see today as the cosmic microwave background, the faint glow of the universe at the moment it first became transparent. After that, the universe enters what astronomers call the cosmic dark ages. There are no stars yet. There are no galaxies. There is just a thin fog of neutral hydrogen and helium gas expanding into the darkness, slowly cooling, very slowly clumping under the influence of gravity and the gravitational scaffolding of dark matter. This period lasts for hundreds of millions of years. The first stars, the so-called population 3 stars, are believed to have formed somewhere between 100 and 200 million years after the Big Bang. These first stars would have been enormous, hundreds of times the mass of the Sun, burning hot and fast, made entirely of hydrogen and helium because no heavier elements existed yet. They would have lived for only a few million years before exploding as supernovas, scattering the first traces of heavier elements into the surrounding gas. From those scattered elements, the next generations of stars would form, and eventually those stars would gather into the first proto-galaxies. But the key word in all of this is slow. The whole process is supposed to be slow. By 280 million years after the Big Bang, the universe should still be in the early throes of structure formation. The first galaxies should be small, dim, only beginning to assemble themselves. They should contain almost no heavy elements because the previous generations of stars have not yet had time to live, die, and seed the surrounding gas with the products of nuclear fusion. They should be surrounded by neutral hydrogen, the cosmic fog that will not fully clear until hundreds of millions of years later in the period called the epoch of reionization. That is the picture Lambda CDM paints. That is what the models predict. MOEM Z14 looks nothing like that. It is bright. Its ultraviolet luminosity corresponds to an absolute magnitude of about -20.2, which makes it as luminous as some of the brighter galaxies in the much later universe. It is compact. Its effective radius is just 74 parsecs, which translates to about 240 light-years. For comparison, the Milky Way is 100,000 light-years across. The distance from our Sun to the galactic center is 26,000 light-years. MOEM Z14 is small enough that you could fit it inside a single spiral arm of the Milky Way with room to spare. But this small, bright object is producing as much ultraviolet light as a galaxy thousands of times its physical size. Something about the way stars are forming inside it, or the way matter is being concentrated in its core, is operating at an efficiency that defies every model of early star formation we have. And then there is the chemistry. The spectroscopic analysis revealed elevated levels of nitrogen. Nitrogen is not a primordial element. It is not produced in the Big Bang. The Big Bang produces hydrogen, helium, and trace amounts of lithium, and that is essentially it. Every nitrogen atom in the universe, including the nitrogen in the air you are breathing right now, was forged inside a star. Specifically, nitrogen is produced through what astronomers call the carbon-nitrogen-oxygen cycle, a sequence of nuclear reactions that happens in the interiors of stars, more massive than the Sun. The carbon needed to start that cycle has to come from earlier generations of stars. So nitrogen requires at least 2 generations of stars to live and die before it can accumulate in significant quantities. And those generations of stars require time. They require the gas they form from to be enriched by previous stellar deaths. The presence of nitrogen in MOEM Z14 at 280 million years after the Big Bang means that the stellar life cycle has already been running there with extraordinary speed. Multiple generations of stars have lived and died and seeded the gas in this tiny galaxy with the chemical signatures of mature stellar evolution. And this is happening when the universe itself is younger than the age of the dinosaurs. There is one more anomaly, and it might be the most striking of all. MOEM Z14 appears to have begun clearing the cosmic fog around it. The epoch of reionization is the period when the universe transitions from a state of mostly neutral hydrogen gas to a state of mostly ionized plasma. It happens because the first generations of stars and galaxies produce ultraviolet radiation, and that radiation is energetic enough to strip electrons from hydrogen atoms, breaking them into protons and free electrons. When enough of this happens across enough of the universe, the cosmic fog clears and the universe becomes transparent to ultraviolet light. Reionization is believed to have begun somewhere around 200 million years after the Big Bang, and to have completed around 1 billion years after the Big Bang. At a redshift of 14, the universe should be almost entirely neutral. Almost all of the hydrogen should still be in its unionized state. The fog should be thick, but the spectrum of MOEM Z14 shows clear evidence that the immediate vicinity of the galaxy has been at least partially ionized. Something inside that galaxy, or some population of objects associated with it, is producing enough ionizing radiation to carve out a transparent bubble in the surrounding hydrogen. This is not supposed to be happening yet. The amount of ultraviolet radiation required to ionize a region of space that large at that early an epoch implies a level of stellar activity that, again, our models did not anticipate. Jacob Shen, a postdoctoral researcher at MIT and one of the authors of the MOEM Z14 paper, put it diplomatically. There is a growing chasm between theory and observation related to the early universe, he said. Growing chasm is academic language for crisis. Because MOEM Z14 is not an isolated outlier, it is the most extreme example, but it is not alone. It sits at the top of a long and rapidly growing list of galaxies that should not exist. Consider Zulong. This is a galaxy that was confirmed in 2025 at a redshift of about 5.2, which places it about 1 billion years after the Big Bang. 1 billion years sounds like a long time. By human standards, it is unimaginably long. By cosmological standards, in the context of how galaxies are supposed to form, it is barely an eye blink. And yet Xulong is a fully formed spiral galaxy. It has a mature central bulge. It has clearly defined spiral arms. It has a total stellar mass of approximately 100 billion solar masses, comparable to the Milky Way itself. It looks, in every visible respect, like a galaxy that has had 10 or 12 billion years to evolve. It has had 1 billion. The Milky Way needed essentially the entire age of the universe to develop the structure it has today. Xulong appears to have done it in less than 1/10 of that time. And Xulong is not unique either. The James Webb Space Telescope has been finding mature-looking spiral galaxies at red shifts that, according to the standard story, should be impossibly early. The structures are too settled. The bulges are too developed. The chemistry is too rich. The stellar masses are too high. Something about the way galaxies actually formed in the early universe is not captured by the models. The instinct to suspect measurement error has now been thoroughly exhausted. The red shifts have been confirmed spectroscopically. The masses have been measured by multiple independent techniques. The morphologies have been examined by teams across different institutions using different analysis pipelines. The results hold. The galaxies are real. They are where Webb says they are. They look the way Webb says they look. The problem is not with the telescope, the problem is with the theory. And the theory in question is not some minor side branch of cosmology. It is the central pillar of the standard model. It is lambda-cold dark matter, the framework that has organized our understanding of the universe for 25 years. It is the model that predicts the patterns in the cosmic microwave background to extraordinary precision. It is the model that explains the large-scale structure of the cosmic web. It is the model that has anchored every cosmology textbook written since the late 1990s. And it is now being asked to explain galaxies that, according to its own rules, should not exist. So far, it cannot. The list of proposed solutions is long and growing. Some researchers have suggested that star formation in the early universe was simply much more efficient than the models assumed. Perhaps the conditions of the dense, hot, low metallicity gas that filled the early universe allowed stars to form more rapidly and in greater numbers than they do in the modern universe. If that is true, then galaxies could have assembled their stellar populations much faster, accounting for the high luminosities Webb is observing. The problem with the solution is that no one has been able to identify a specific physical mechanism that would produce the required efficiency. Star formation in the modern universe is regulated by a delicate balance of gas pressure, magnetic fields, turbulence, and radiation feedback. Changing that balance enough to produce a 100-fold increase in efficiency requires changes to physics that are not, as far as we can tell, present in the standard model. Other researchers have proposed that the initial mass function of the first stars was top-heavy, meaning that the first generations of stars were much more massive than the typical stars that form today. A top-heavy initial mass function would produce far more ultraviolet light per unit of stellar mass formed, which would account for the high luminosities. It would also produce heavy elements much faster, which could account for the elevated nitrogen levels in galaxies like MOMZ14. The problem here is that while a top-heavy initial mass function is plausible for the very first generation of stars, it requires that the conditions producing it persisted longer and applied to more star formation than the standard picture predicts. Other proposals invoke entirely new physics. Early dark energy is one such proposal. The idea is that a brief burst of additional dark energy existed in the universe before recombination, before the cosmic microwave background was released. This extra energy would have altered the expansion rate of the early universe in ways that could explain both the early galaxy problem and the Hubble tension, the unrelated but equally serious crisis in modern cosmology. But early dark energy models have their own difficulties. They tend to fit one observation while contradicting another. Modifications to dark matter have also been proposed. Perhaps dark matter is warmer than the cold dark matter assumed in the standard model. Perhaps it interacts with itself in ways that allow it to form denser concentrations faster than expected. Perhaps it has properties that allow galaxy formation to accelerate in the early universe. Each of these proposals can solve part of the problem. None of them so far solve all of it. What is becoming increasingly clear, however, is that the standard model in its current form is not sufficient. The chasm between theory and observation that Jacob Shen mentioned is not a small one, and it is not closing with refinements. Every new James Webb data release widens it. Every new spectroscopic confirmation of an impossible galaxy reinforces the conclusion that the early universe was doing things that our best models did not anticipate, and these galaxies are not the only problem. They are part of a broader pattern of anomalies that is emerging across cosmology in real time. The Hubble tension is another piece of the same puzzle. For more than a decade, two methods of measuring the expansion rate of the universe have been giving two different answers. The early universe method, which uses the cosmic microwave background and the lambda CDM model to calculate what the expansion rate should be today, consistently produces a value of about 67 kilometers per second per megaparsec. The late universe method, which uses the cosmic distance ladder to measure the expansion rate directly in the nearby universe, consistently produces a value closer to 73, and in some recent measurements as high as 76. The gap between these two values, once dismissed as likely the result of measurement error, has now been confirmed to a statistical significance of 5 sigma. In particle physics, 5 sigma is the threshold at which a discrepancy is no longer attributable to chance. It is the threshold used to declare a discovery. The Hubble tension has crossed that threshold. Something real is going on. Something in our model of how the universe expands is not quite right. And whatever it is connected to the early universe in ways that the impossible galaxies are forcing cosmologists to take seriously. The Webb findings are not a curiosity. They are not a footnote. They are a sustained, repeated, statistically robust signal that something about our understanding of the early universe is incomplete. Daniel Skolnick, the cosmologist at Duke University whose team has been leading some of the recent Hubble constant measurements, has been blunt about what this means. He has said that the community needs to start treating these tensions as the serious crises they are. He has said that the standard model of cosmology, the model that has survived every test for 25 years, may now be cracking, and he is not alone in saying it. At the Tensions in Cosmology 2025 conference, held in Corfu, Greece, more than 130 researchers gathered to discuss the growing list of anomalies. The conference report, published in early 2026, made it clear that the field is at a turning point. The era of confident, settled cosmology is over. The era of new fundamental physics may be beginning. To understand the scale of what is being challenged, you have to understand what lambda CDM actually claims. The model is built on a few core assumptions, each of them strongly supported by decades of observation, each of them now under pressure from the James Webb data. The first assumption is that the universe is homogeneous and isotropic on large scales, meaning that on scales of hundreds of millions of light-years and larger, the universe looks the same in every direction and from every vantage point. The second is that the dominant component of matter in the universe is cold dark matter, a form of matter that interacts only through gravity and moves slowly compared to the speed of light. The third is that the dominant component of energy in the universe today is dark energy, a mysterious form of energy whose density remains roughly constant as space expands, and which is currently driving the accelerated expansion of the cosmos. The fourth is that the universe underwent a period of cosmic inflation in the first tiny fraction of a second after the Big Bang, an exponential expansion that smoothed out initial irregularities and stretched quantum fluctuations to cosmic scales, providing the seeds for all subsequent structure formation. From these assumptions, the model makes predictions about everything from the patterns in the cosmic microwave background to the distribution of galaxies on the largest scales, to the abundance of light elements like hydrogen and helium and lithium. And for 25 years, those predictions have matched observations to remarkable precision. The cosmic microwave background, mapped first by the COBE satellite, then by WMAP, then by the Planck mission, shows exactly the patterns that lambda CDM predicts. The large-scale structure of the universe, mapped by surveys like the Sloan Digital Sky Survey, matches the model's predictions. The abundance of light elements, measured in the spectra of ancient stars and intergalactic gas clouds, matches the model's predictions. Lambda CDM has been one of the most successful theories in the history of physics, until now. The James Webb findings are not the only pressure on the model. They are perhaps the most visible, the most dramatic, the most easily communicated to the public. But they sit alongside the Hubble tension, alongside the growing list of small but persistent anomalies in the cosmic microwave background, alongside the tensions and measurements of how clumpy matter is on large scales, alongside hints from the dark energy spectroscopic instrument that dark energy itself may not be perfectly constant after all. Every one of these tensions taken alone has a possible mundane explanation. Maybe there is a measurement error somewhere. Maybe there is a calibration issue. Maybe there is some subtle source of systematic uncertainty that has been overlooked. But when you stack the tensions on top of each other, when you see them all pointing in similar directions, when you watch them grow stronger with every new data set rather than weaker, the pattern starts to look like something other than coincidence. It starts to look like a model that is reaching the limits of what it can explain. So tonight, we are going to follow the light from MOMZ14 backwards through space and time, and we are going to see what it has to tell us about the universe at its very beginning. We are going to look at the other impossible galaxies Webb has found and what they reveal about how structure actually formed in the early cosmos. We are going to confront the possibility that the standard model is breaking, and we are going to ask what might replace it. We are going to descend into the deepest mysteries of cosmology, into dark matter and dark energy, into the cosmic microwave background and the epoch of reionization, into the question of whether the universe began the way we think it did, or whether the story we have been telling ourselves for a quarter of a century is missing something fundamental. And by the end, we will have to confront the most uncomfortable possibility of all. That when we look at the edge of the universe, what we are really seeing is the edge of our own understanding. That the wall at the end of our vision is not a wall around the cosmos, it is a wall around our knowledge. And that the universe on the other side of that wall is stranger, older, and more inexplicable than anything our models have prepared us for. But before we go further, before we follow the light back through 13.5 billion years of expanding space, we have to understand where the light is coming from. We have to understand what it means for an object to be at the edge of the universe. Because the edge is not what most people think it is. The edge is not a wall. It is not a barrier. It is not the place where the universe stops. The edge is a horizon defined not by space but by time, by the speed of light, by the age of the cosmos itself. To stand at the edge of the universe is to stand at the boundary of what light has had time to deliver to us. And what light has delivered to us, in this last handful of years since the James Webb Space Telescope began its observations, is a message that is forcing us to rewrite the story of how everything began. When astronomers talk about the edge of the observable universe, they are not pointing to a place, they are pointing to a moment. The edge is the boundary of what light has had time to reach us from. Light moves at a finite speed, 300,000 kilometers per second, which sounds impossibly fast until you remember that the universe is impossibly large. A photon emitted from the surface of the Sun takes 8 minutes to reach Earth. A photon emitted from the nearest star takes 4 years. A photon emitted from the center of our galaxy takes 26,000 years. A photon emitted from Andromeda takes 2.5 million years. And a photon emitted from the most distant galaxy Webb has confirmed takes more than 13 billion years. The universe is so large that light, the fastest thing that exists, cannot cross it in the lifetime of the universe itself. There are regions of space whose light has never reached us and never will. Those regions are real. They exist. We just cannot see them, because their light is still in transit, or because the space between us has been expanding faster than light can cross it. The edge of the observable universe is the boundary defined by the age of the cosmos and the speed of light together. We see as far as light has had time to travel. Anything beyond that boundary is, for us, invisible. Not because it is hidden, not because it is dark, but because the universe has not been around long enough for its light to arrive. This is why the edge of the universe is a kind of time machine. To look at MOMZ14 is to look at the universe as it was 280 million years after the Big Bang. To look at the cosmic microwave background, the faint glow of microwave radiation that fills the sky in every direction, is to look at the universe as it was 380,000 years after the Big Bang. when the plasma first became transparent and the first photons were released. There is nothing older than the cosmic microwave background that we can see in light. Before that moment, the universe was opaque. Photons could not travel freely. They were scattered constantly off free electrons in the hot, dense plasma, like sunlight scattering off the molecules in a thick fog. To look back beyond the cosmic microwave background would require some other messenger, gravitational waves perhaps, or neutrinos, particles that interact so weakly with matter that they could have escaped from the early plasma and traveled freely through the subsequent 13.5 billion years. We do not yet have instruments sensitive enough to detect those primordial gravitational waves or that primordial neutrino background. So the cosmic microwave background is, for now, the wall. It is the oldest light. It is the surface of last scattering. Beyond it lies the time before light could move, and we cannot see into that time directly. We can only infer. But here is what is remarkable. The space between us and the cosmic microwave background is not empty. It is filled with galaxies, gas clouds, intergalactic plasma, dark matter, dark energy. It is filled with 13.5 billion years of cosmic history. And as light from the cosmic microwave background travels across that space toward us, it interacts with everything along the way. It picks up information about the structures it passes through. Astronomers can use those interactions to map the matter between us and the surface of last scattering. They can use the way the microwave photons are distorted by gravitational lensing to measure the distribution of dark matter. They can use the way the photons are slightly shifted in energy by their passage through hot intergalactic gas to identify clusters of galaxies. The cosmic microwave background is not just a snapshot of the early universe. It is a probe of everything that has happened since. And what the cosmic microwave background tells us about everything that has happened since is starting to disagree with what Webb is telling us about how galaxies actually formed. The cosmic microwave background reveals a universe that was almost perfectly uniform 380,000 years after the Big Bang. The temperature varies by only about 1 part in 100,000 across the sky. The density variations were similarly tiny. These tiny variations are the seeds from which all later structure grew. Gravity amplified them over billions of years, turning regions that were 1 part in 100,000 denser than average into the galaxies, galaxy clusters, and filaments of the cosmic web. According to Lambda CDM, this process should have produced a specific timeline. By 200 million years after the Big Bang, the first stars should be lighting up. By 500 million years after the Big Bang, the first proto-galaxies should be forming. By 1 billion years after the Big Bang, recognizable galaxies should be assembling, though still small and irregular compared to their modern counterparts. By 2 or 3 billion years after the Big Bang, the first mature spiral and elliptical galaxies should be appearing. By the time the universe is 5 or 6 billion years old, the universe should look more or less like a younger version of the universe we see today, with galaxies of recognizable types distributed in patterns that match the modern cosmic web. That timeline matches what older telescopes saw. Hubble, in the deep field images it captured starting in the 1990s, observed galaxies at redshifts that placed them several billion years after the Big Bang. Those galaxies looked younger than modern galaxies. They were more irregular, more chaotic, with active star formation and less developed structure. They were consistent with the picture that Lambda CDM painted. But Hubble could not see past a certain point. Its instruments were not sensitive enough to detect galaxies at redshifts much higher than 10. The earliest era of galaxy formation, the era between 100 million and 500 million years after the Big Bang, was hidden from Hubble's view. That era was Webb's territory, and what Webb is finding there is breaking the timeline. The pattern in Webb's discoveries is consistent. The galaxies it finds at the highest redshifts are too bright, too massive, too chemically enriched, and too structurally complete. They look like galaxies that have had billions of years to evolve, but they exist at a time when only a few 100 million years have passed, and the discrepancy is not subtle. It is not a matter of galaxies being 20% more massive than predicted, or 50% brighter. It is a matter of galaxies being orders of magnitude more luminous than expected, with stellar masses that should have required 10 times the available time to assemble. It is a matter of finding nitrogen and carbon and oxygen in objects that should have contained only hydrogen and helium. It is a matter of finding mature stellar populations where we expected to find only primordial fireballs. And every time astronomers go back to verify a result, the result holds. The galaxies are real. The redshifts are correct. The masses, the luminosities, the chemical compositions are all confirmed. The universe is not behaving the way the standard model says it should have behaved. To make sense of this, you have to think about what galaxy formation actually requires. A galaxy is not a simple thing. It is not a cloud of gas that suddenly congeals into a star factory. It is the end product of a long, complex, multi-stage process that involves gravity, gas dynamics, radiation, magnetic fields, and feedback from generations of stars. The first step is gravitational collapse. A region of space slightly denser than average begins to pull surrounding matter toward itself. Most of the matter that falls in is dark matter, which does not interact with radiation and can therefore collapse freely. The dark matter forms a halo, a roughly spherical concentration of mass held together by its own gravity. The dark matter halo creates a gravitational well, and ordinary baryonic matter, hydrogen and helium gas, begins to flow into it. As the gas falls into the well, it heats up. To form stars, the gas must cool. It must radiate away its thermal energy so that gravity can compress it further. Different elements have different cooling efficiencies. Hydrogen and helium, the only elements present in significant amounts in the primordial universe, are inefficient coolants. They struggle to radiate away energy quickly enough to allow rapid star formation. Heavier elements, especially carbon and oxygen, are much more efficient coolants. They can radiate energy across a much wider range of wavelengths. This is one of the reasons why star formation is supposed to be slow in the early universe. The gas is too clean. It does not have the heavy elements that allow it to cool efficiently. So the gas takes a long time to collapse, and stars take a long time to form. The first generation of stars, the population 3 stars, are believed to have been very massive precisely because primordial gas cannot cool efficiently. Only large clouds can collapse, producing only large stars. These first stars, once they form, change everything. They emit intense ultraviolet radiation, which ionizes the surrounding gas and prevents nearby gas clouds from collapsing into more stars. They also live short lives. A star 100 times the mass of the Sun burns through its fuel in only a few million years. When it dies, it explodes as a supernova, scattering heavy elements into the surrounding gas. Those heavy elements eventually enrich the gas, making it more efficient at cooling, which allows subsequent generations of stars to form more rapidly. This is the chain of cause and effect that is supposed to govern galaxy formation in the early universe. First, dark matter halos collapse. Then, primordial gas flows into the halos. Then, the first generation of massive stars forms. Then those stars die and enrich the gas with heavy elements. Then subsequent generations of stars form more quickly and in greater numbers. Then galaxies assemble, grow, merge, and evolve. The whole process is supposed to be limited by the speed of stellar evolution and by the gradual enrichment of the gas. And the speeds involved are slow on cosmological scales. The first significant enrichment of the cosmic gas should not occur until the first generation of massive stars has lived and died, which takes at least a few million to tens of millions of years. The second generation of stars then forms from the enriched gas, lives, dies, and produces further enrichment over additional tens to hundreds of millions of years. By 280 million years after the Big Bang, you would expect a galaxy to have gone through, at most, a few generations of stellar evolution. The amount of nitrogen, carbon, and oxygen present in the gas should be very small. MOM-Z14 contradicts this. The elevated nitrogen levels suggest that multiple generations of stars have already lived and died there. The compact size, just 240 light-years across, suggests that the stars are crammed into a very small volume, which would imply extraordinary stellar densities. The high ultraviolet luminosity suggests an enormous population of hot, massive young stars. Putting it all together, what MOM-Z14 looks like is not a primitive proto-galaxy. It looks like a fully functional star factory that has been operating at high efficiency for some time, with a stellar mass and chemical enrichment that defies what we thought 280 million years could produce. And the question that is now being asked across the field of cosmology is, what physical mechanism could explain this? The proposals are numerous and increasingly creative. Some researchers have suggested that the first generation of stars was even more extreme than current models assume. Perhaps the population 3 stars were not just 100 times the mass of the Sun. Perhaps some of them were 1,000 times the mass of the Sun, or 10,000. Such supermassive stars, if they existed, would have produced enormous amounts of heavy elements through exotic nuclear processes, and they would have collapsed directly into black holes when they died, providing the seeds for the supermassive black holes we see at the centers of galaxies today. The direct collapse scenario, as it is called, has been around for years as a possible explanation for the early appearance of supermassive black holes. The Webb findings are giving it new urgency. Other researchers have proposed that the rate of star formation in the early universe was simply much higher than in the modern universe. Star formation rate is one of the key parameters in cosmological simulations, and it is usually calibrated against observations of nearby galaxies. But there is no a priori reason that the star formation rate had to be the same in the early universe as it is today. The conditions were very different. The gas was denser. The dark matter halos were more compact relative to the gas they contained. The radiation environment was different. Magnetic fields were different. Perhaps in those conditions, gas could fragment into stars much more rapidly than it does today. If the early star formation efficiency was 10 times higher than current models assume, that alone would go a long way toward explaining the Webb findings. The galaxies would be brighter because they would have more massive stellar populations. They would be more chemically enriched because more stars would have lived and died in less time. They would be more structured because the cycle of star formation, death, and reformation would have progressed further than the standard timeline predicts. But high-efficiency star formation is not free. It has implications for the larger universe. It would mean that the cosmic budget of ultraviolet light produced by the first galaxies was much larger than expected, which would have implications for the timing of reionization. It would mean that the cosmic budget of supernova explosions was much larger than expected, which would have implications for the chemical enrichment of intergalactic gas. It would mean that the cosmic budget of massive black hole formation was much larger than expected, which would have implications for the existence and growth of supermassive black holes in the early universe. Speaking of supermassive black holes, they are part of the same puzzle. Webb has not only found galaxies at high red shifts that should not exist, it has found supermassive black holes at high red shifts that should not exist. Black holes with masses of 1 million or 1 billion solar masses have been detected in galaxies as early as a few 100 million years after the Big Bang. The problem is that black holes grow by feeding. They consume surrounding matter, and the matter spirals into them, releasing energy in the form of radiation. The Eddington limit, named after the astrophysicist Arthur Eddington, sets a theoretical cap on how fast a black hole can grow. The cap exists because as matter spirals in and releases radiation, the radiation pushes back against more infalling material. There is a balance between gravity pulling matter in and radiation pressure pushing it out, and that balance limits the rate at which the black hole can accrete mass. Even feeding at the Eddington limit continuously for the entire age of the early universe, a black hole that started as a stellar mass remnant of about 100 solar masses could only grow to perhaps 1 million solar masses by 800 million years after the Big Bang. Beyond that, the math runs out of time. And yet Webb has found supermassive black holes that have masses of hundreds of millions or billions of solar masses at red shifts that correspond to less than 1 billion years after the Big Bang. They should not have been able to grow to that mass that quickly. Either the seeds they started from were much larger than stellar mass remnants, which means something exotic was happening in the early universe to produce them, or they were able to accrete matter at rates above the Eddington limit, which means something exotic was happening in their accretion physics. Neither option is comfortable. Both require additions to the standard picture. The direct collapse scenario reappears here. If the first generation of stars included objects so massive that they collapsed directly into black holes without going through a supernova phase, those black holes could have started with masses of thousands or even 100,000 solar masses. Starting from a larger seed, it becomes easier to grow to supermassive sizes within the available time, The direct collapse scenario is not confirmed, but Webb has been finding evidence that is increasingly consistent with it. Some of the objects Webb has detected at high red shifts are extremely compact and luminous in ways that are consistent with feeding supermassive black holes. The team that analyzed MOMZ14 noted that the morphology of the galaxy, its compactness and high luminosity, is at least suggestive of the presence of a central massive black hole. They could not confirm it from the available data, but they could not rule it out either. The possibility that the universe at 280 million years old already had a population of supermassive black holes feeding voraciously at the centers of its first galaxies is, frankly, staggering. It implies that the entire chain of cosmic evolution we have been telling ourselves about, the slow buildup of structure from primordial fluctuations to the modern universe, may have a missing chapter at the very beginning. A chapter in which something happened that we have not accounted for. A chapter in which the seeds of cosmic structure were laid down with an efficiency and a speed that our models did not anticipate. This brings us back to the broader question. What is going on at the edge of the universe? What is Webb really showing us? The most conservative interpretation is that lambda CDM is essentially correct, but requires modifications at the early end. The early universe was more active, more efficient, more productive than the simplest models assumed. Stars formed faster, black holes formed earlier, galaxies grew more rapidly. The general framework of the standard model survives, but the specific timeline needs adjustment. This is the interpretation many cosmologists prefer, because it preserves the successes of lambda CDM while accommodating the new observations. The harder interpretation is that lambda CDM has a deeper problem. That the assumptions on which it is built, perhaps about the nature of dark matter, perhaps about the nature of dark energy, perhaps about the conditions that prevailed at the beginning of the universe, are not quite right. That what Webb is showing us is the first observational evidence that we need a new physical framework, one that goes beyond the standard model. This interpretation is more disruptive, but it is being taken increasingly seriously. The combination of the early galaxy problem, the Hubble tension, the hints of evolving dark energy from recent measurements, and the persistent anomalies in the cosmic microwave background is adding up to a pattern. And the pattern points towards something missing. Some theorists have begun to revive ideas that were once considered fringe. The possibility that the universe is not perfectly homogeneous on the largest scales, for instance, has long been a minor strand of cosmological thought. The standard model assumes the cosmological principle, the idea that the universe looks the same in every direction and from every location when viewed on sufficiently large scales. This assumption is well supported by observations, but it is an assumption nonetheless. If the universe is actually significantly inhomogeneous on large scales, if there are regions where conditions differ substantially from the average, then many of the tensions in modern cosmology could be partially explained as artifacts of our specific location. The KBC void hypothesis, the idea that the Milky Way sits inside a large underdense region, is one example of this kind of thinking. If we live in a void, then the local expansion rate would naturally appear higher than the cosmic average, which could explain the Hubble tension. But the void hypothesis does not easily explain the early galaxy problem. The galaxies Webb is finding are at distances of 13 billion light-years. They are not in our local volume. They are in regions that should be representative of the average early universe. If those representative regions are producing galaxies that violate the standard timeline, the problem is not local, it is universal. Other theorists have proposed modifications to gravity itself. Modified Newtonian dynamics, MOND, and its various relativistic extensions have been around for decades as alternatives to dark matter. The idea is that what we observe as gravitational anomalies in galaxies and galaxy clusters is not the result of invisible matter, but of gravity behaving differently than Newton or Einstein predicted in certain regimes. MOND has had some success at the scale of individual galaxies, but has struggled at the scales of galaxy clusters and the cosmic web. Modified gravity theories have not, in general, been able to replace dark matter as a comprehensive explanation for the universe's structure. But the Webb findings have led some researchers to wonder whether modifications to gravity in the very early universe might explain the early galaxy problem. If gravity was effectively stronger in the conditions of the early cosmos, structures could have formed faster. The mathematical details of how this would work and what it would imply for other observations are still being worked out. But the fact that mainstream researchers are now seriously discussing modified gravity in connection with the early universe is itself a measure of how unsettled the field has become. Even more radical proposals are being floated. Some researchers have suggested that the cosmological constant, the term in Einstein's equations that represents dark energy, may not actually be constant. The Dark Energy Spectroscopic Instrument, which has been mapping the distribution of galaxies and quasars across enormous volumes of the universe, has produced data that hints, though does not yet confirm, that dark energy may be weakening over cosmic time. If dark energy is indeed evolving, it would represent a major departure from the standard picture. It would mean that one of the most basic assumptions of lambda CDM, the constancy of the cosmological constant, is wrong. And the implications would cascade through the entire field. The future of the universe would change. The fate of cosmic expansion would change. The interpretation of the cosmic microwave background and of the large-scale structure would change. The hint of evolving dark energy is currently at a statistical significance of around 3 to 4 sigma, which is suggestive but not yet decisive. Further data from ongoing surveys will either strengthen or weaken the signal. But, like the other tensions in modern cosmology, it is not going away with refinement. It is becoming more persistent. The combination of all these threads, the early galaxy problem, the Hubble tension, the evolving dark energy hints, the cosmic microwave background anomalies, the unexpected mass and structure of high redshift supermassive black holes, is producing a sense of accumulating crisis in the field. The accumulating crisis is what makes this moment in cosmology genuinely historic. We are likely watching, in real time, the breakdown of a major scientific paradigm, not because the old paradigm was wrong in everything it said, but because it is showing the limits of its applicability. The standard model of cosmology was constructed during a particular era of observational capability, an era when our telescopes could see only so far back, when our instruments could measure only certain quantities, when our datasets were of certain sizes. As those capabilities have expanded, as Webb has opened a window onto a previously inaccessible era of the universe's history, as DESI and Euclid and the Roman Space Telescope and other instruments are accumulating data of unprecedented precision, the cracks in the old model are being exposed. The cracks were always there, but we could not see them. Now we can, and the question is what we build in their place. To understand the magnitude of what is being challenged, you have to step back and consider what lambda CDM has done for cosmology. Before lambda CDM, the field of cosmology was speculative in a way that is hard to appreciate today. There were competing ideas about whether the universe had a beginning at all. There were competing ideas about whether it was finite or infinite, whether it had positive or negative curvature, whether it would expand forever or eventually recollapse. The combination of the cosmic microwave background measurements from COBE, WMAP, and Planck, along with Type Ia supernova observations, large-scale structure surveys, and other lines of evidence, brought all of these questions to convergence. By the early 2000s, cosmology had become precision science. The age of the universe was known to within a few tens of millions of years. The composition of the universe was known to within a few percent. The geometry of the universe was known to be flat to high precision. The framework that achieved this convergence was lambda CDM. It was an enormous accomplishment. It transformed cosmology from a speculative discipline into a quantitative one. And it is that framework that is now showing signs of strain. When cosmologists talk about the standard model being challenged, they are not talking about minor adjustments. They are talking about the possibility that some of the deep assumptions of the framework, some of the things that 25 years of precision data seemed to confirm, may need to be revised. That possibility is exhilarating and terrifying in equal measure. It is exhilarating because it means there is new physics waiting to be discovered, deeper layers of reality waiting to be uncovered. It is terrifying because it means that the confident picture of the universe we have built over the last quarter century may be incomplete in ways we are only beginning to grasp. What Webb is showing us at the edge of the universe is, in this sense, more than a series of bright galaxies. It is a message from the boundary of our knowledge. It is saying that the edge of the observable universe is closer in time to a regime where physics behaves in ways our models do not yet capture. It is saying that the first few 100 million years of cosmic history are stranger than we thought. It is saying that the foundations on which we have been building our picture of the universe may need to be rebuilt. And the strangeness does not stop at the bright galaxies. Webb is also finding things at the edge of the universe that are dimmer, more subtle, and in their own way just as challenging. It is finding evidence of cosmic dust at red shifts, where dust was not supposed to exist yet. Cosmic dust, the small solid particles that pervade the interstellar medium, is produced primarily by stars at the end of their lives. Old stars, dying in the slow processes of mass loss from red giants and asymptotic giant branch stars, produce a particular kind of dust. Younger stars dying in supernova explosions produce a different kind of dust. Both processes require time. Dust should not be present in significant quantities in galaxies that are only a few 100 million years old. And yet Webb has detected the spectroscopic signatures of dust in galaxies at redshifts as high as 8, 9, even 10. The dust is there, it is being detected, and it should not be. Something is producing it on timescales that our models say are too short. Webb is also finding hints of strange structures at the edge of the universe. There are reports of galaxy candidates that seem to be unusually clustered, suggesting that the cosmic web of large-scale structure may have formed earlier and more strongly than predicted. There are reports of galaxies that show evidence of having undergone repeated mergers, despite the fact that the universe was young enough that such mergers should have been rare. There are reports of galaxies with morphological features, bars, rings, even hints of spiral structure, at redshifts where such features were not expected to exist at all. The picture that is emerging is of an early universe that was richer, more diverse, more structurally complex than the standard model allowed. There is one more discovery that deserves attention because it speaks directly to the question of what was happening in the first moments after the Big Bang. Webb has been observing the spectra of distant quasars, the brilliantly luminous active nuclei of galaxies powered by feeding supermassive black holes. The light from these quasars passes through enormous volumes of intergalactic gas on its way to us. By analyzing the absorption lines in their spectra, astronomers can probe the conditions of the intergalactic medium across cosmic time. The data from Webb is showing that the epoch of reionization, the period when the universe transitioned from neutral to ionized, was more complex and patchier than previous models suggested. Reionization did not happen uniformly, it happened in pockets, with some regions becoming transparent much earlier than others. This patchiness is consistent with the idea that the first galaxies were producing more ultraviolet radiation than expected, but it is also raising questions about what specific objects were doing the ionizing. Were they galaxies? Were they quasars? Were they some combination? Were there sources of ionizing radiation that we have not yet identified? All of these threads, the bright galaxies, the early black holes, the unexpected dust, the early structural complexity, the patchy reionization, point toward an early universe that was already in many ways like the modern universe, only more compressed in time. The slow buildup of structure that Lambda CDM predicts does not seem to match what Webb is observing. Whatever was happening in the first few 100 million years was faster, more intense, more productive than the standard model allowed. And the question of why, the question of what physical mechanisms were at work, is now one of the central questions in cosmology. The answers, when they come, will reshape our understanding of how the universe works. But we are not at the answers yet. We are at the questions. And the questions are leading us into deeper territory, into the very nature of the first moments after the Big Bang, into the role of inflation, into the seed fluctuations that gave rise to all subsequent structure. The story Webb is telling is not just about the edge of the universe, it is about the beginning of the universe. It is about what happened in the first second, the first millisecond, the first fraction of a second after time itself began. Because if galaxies are forming faster than expected at 280 million years after the Big Bang, then the conditions that allowed them to form must have been laid down even earlier. The seeds must have been planted in an even earlier era. The fluctuations that grew into the impossible galaxies of Moem Z14 and Zulong and their hundreds of cousins must have been imprinted on the universe in the period of cosmic inflation, the unimaginably brief moment of exponential expansion that is believed to have occurred in the first tiny fraction of a second after the Big Bang. And whatever happened then, whatever determined the initial conditions of the universe, must contain the explanation for what Webb is now revealing. To understand the edge of the universe, then, we have to go back further. We have to go back to the very beginning. We have to go back to inflation, and to the question of what set the universe in motion with the properties it now seems to have. And there, at the very root of cosmic history, lies a mystery even deeper than the one Webb has uncovered. Cosmic inflation is one of those ideas in physics that feels too strange to be true, and yet has survived every observational test we have managed to throw at it. The theory was proposed in the early 1980s by the physicist Alan Guth, working at the time on problems in particle physics. He was not initially trying to solve a problem in cosmology. He stumbled into it. He was thinking about phase transitions in the early universe, the moments when the cooling cosmos passed through critical thresholds and the laws of physics themselves underwent fundamental changes. And he realized that if a certain kind of quantum field, a scalar field with the right properties, dominated the energy of the universe during one of those transitions, the universe would have undergone an extraordinarily brief but extraordinarily violent period of exponential expansion. In a time so short that the human mind cannot meaningfully process it, perhaps 10 to the negative 35th of a second, the universe would have grown by a factor of at least 10 to the 26th power. A region smaller than a single proton would have expanded to something larger than the entire observable universe today. Inflation, Guth realized, would solve several problems in cosmology that have been bothering theorists for years. It would explain why the universe looks so uniform across its largest scales. It would explain why the geometry of the universe is flat. It would explain why we do not see exotic relics, magnetic monopoles, and topological defects that would otherwise have been produced in the early universe. Inflation would, in one stroke, dissolve a half-dozen mysteries that had nagged at cosmology for decades. The theory was bold. It required physics we did not yet understand. It required a field, the inflaton, that we have never directly detected. It required the universe to have undergone, in its first instant, an episode of expansion so extreme that it borders on the absurd. And yet, over the subsequent decades, observation after observation has confirmed the basic predictions of inflation. The cosmic microwave background has the patterns inflation predicts. The distribution of galaxies on the largest scales matches what inflation says it should be. The flatness of the universe is exactly what inflation requires. The statistical properties of the fluctuations that seeded all structure formation are precisely what inflation produces. Today, cosmic inflation is the leading framework for understanding the very beginning of the universe. It is not absolutely confirmed. There are still alternative theories, but the weight of observational evidence has been pushing in inflation's direction for 40 years. The reason inflation matters for the story Webb is telling at the edge of the universe is that inflation is what set the initial conditions for everything that came afterward. When inflation ended, the energy that had been driving the exponential expansion was converted into a hot, dense plasma of particles and radiation. This is sometimes called reheating. It is the moment when the universe transitioned from the inflationary phase to the radiation-dominated phase, the moment when conventional Big Bang physics began. The temperature of the post-inflation universe was enormous, perhaps 10 to the 27th degrees Kelvin, hot enough that the fundamental forces of nature had not yet separated into the distinct interactions we observe today. From that incandescent beginning, the universe cooled, expanded, and gradually assembled the structures we see. But everything that came after inflation, every galaxy, every star, every planet, every atom in your body, was shaped by the conditions inflation left behind. The tiny quantum fluctuations that gave rise to galaxies were stretched to cosmic scales during inflation. The smoothness of the universe was imposed by inflation. The flatness of space was imposed by inflation. The very fabric of the cosmos was woven during that unimaginably brief moment when the inflaton field drove space to expand faster than light. So when we look at the impossible galaxies Webb is finding at the edge of the universe, we are looking at the consequences of what happened during inflation. The seeds of those galaxies, the slightly overdense regions of space that would eventually collapse to form them, were laid down in the inflationary era. If the galaxies are forming faster than expected, then either the seeds were larger than expected, or the conditions for their growth were more favorable than expected, or some combination of the two. Both possibilities point back to inflation. This is one of the reasons why some theorists have started taking the early galaxy problem seriously as a signal of new physics in the inflationary era. The standard inflationary models predict a particular kind of fluctuation spectrum. The fluctuations should be very nearly scale invariant, meaning that the amplitude of the fluctuations is roughly the same on all scales. They should be very nearly Gaussian, meaning that their statistical properties follow the standard bell curve distribution. They should be adiabatic, meaning that all components of the universe, ordinary matter, dark matter, radiation, share the same density variations in proportion. These predictions match the observations of the cosmic microwave background to high precision, but they are based on the simplest inflationary models. There are more complex versions of inflation that predict subtle departures from these properties. There are versions in which the fluctuations are not perfectly scale invariant, with slightly more power on small scales than on large scales. There are versions in which the fluctuations are not perfectly Gaussian, with slight tails or asymmetries in their statistical distribution. There are versions in which different components of the universe carry slightly different fluctuation patterns. Any of these departures could have implications for galaxy formation in the early universe. A spectrum with more power on small scales would produce more density fluctuations on the scales relevant to early galaxy formation, leading to galaxies that form earlier and grow faster than the standard model predicts. A spectrum with non-Gaussian features could produce rare, extreme overdensities that collapse into massive galaxies earlier than expected. The Webb findings are giving theorists motivation to look at these more complex models more seriously than they have in decades. But inflation is not the only place where new physics could be hiding. The other major component of the cosmic puzzle is dark matter, and dark matter is intimately connected to the question of how early galaxies formed. Without dark matter, galaxies as we know them could not exist. The gravity of ordinary matter alone is not strong enough to pull gas into the dense concentrations needed for star formation in the available time. Dark matter, which does not interact with radiation and can therefore collapse freely under gravity, builds the gravitational scaffolding into which ordinary matter falls. The dark matter halos form first, and the galaxies form inside them. So the question of how galaxies formed in the early universe is fundamentally tied to the question of how dark matter halos formed in the early universe. And that depends on the properties of dark matter itself. In the standard cold dark matter model, dark matter consists of particles that interact only through gravity and the weak nuclear force. These particles are cold, meaning that they move slowly compared to the speed of light, and that they were already moving slowly at the time when the universe was hot and dense. Cold dark matter produces halos that grow hierarchically, with small halos forming first and merging over time to produce larger halos. The largest halos in the universe today, the ones that host galaxy clusters and superclusters, are the products of billions of years of merger and growth. The smaller halos that host individual galaxies form earlier and faster. According to cold dark matter simulations, the halos massive enough to host galaxies the size of MOMZ14 should not exist 280 million years after the Big Bang. There should not have been enough time for them to grow. The combination of gravitational collapse and hierarchical merging takes time, and 280 million years is not enough. This is one of the most direct tensions between the Webb findings and the standard model. The galaxies Webb is finding require host halos that the simulations say should not yet exist. The discrepancy is not a small one. It is not a matter of the simulations being off by 10 or 20%. It is a matter of the simulations predicting essentially zero galaxies of the type Webb is observing at those red shifts. Some theorists have responded by proposing modifications to the dark matter sector. What if dark matter is not perfectly cold? What if it consists of particles that are warm, moving at significant fractions of the speed of light in the early universe? Warm dark matter would suppress the formation of the smallest halos, but would not significantly change the formation of larger ones. It would not, on its own, explain the early galaxy problem. What if dark matter has self-interactions? What if dark matter particles can scatter off each other with some probability, depositing energy and momentum in a way that changes how halos grow? Self-interacting dark matter has been proposed for years as a way to address other problems in galaxy formation, including the apparent discrepancy between simulated and observed properties of dwarf galaxies. It might also play a role in explaining the Webb findings, though the details are still being worked out. What if dark matter consists of primordial black holes? This is a particularly intriguing possibility. Primordial black holes are hypothetical black holes that could have formed in the very early universe, not from collapsing stars, but from extreme overdensities in the inflationary or post-inflationary era. If a significant fraction of dark matter consists of primordial black holes, then the small-scale structure of dark matter would be different from what the standard cold dark matter model predicts. Galaxies could form around primordial black hole seeds, and the supermassive black holes we see at galaxy centers might be the direct descendants of these primordial seeds. The early appearance of supermassive black holes in Webb data is at least suggestive of this possibility. The early appearance of massive galaxies is consistent with it. Primordial black holes as dark matter is still a minority view in the field, but the Webb findings have given it new energy. There is yet another possibility, and this one cuts even deeper. What if the standard model of cosmology is wrong in some fundamental way that we have not yet articulated? What if the universe is not the homogeneous expanding three-dimensional manifold we have been modeling? What if there is some deeper structure, some hidden symmetry, some unrecognized dimension that becomes relevant in the regime of the early universe? These speculations sound exotic, and they are. But the history of physics is full of moments when the established framework turned out to be a special case of a more general framework. Newtonian mechanics turned out to be the low-velocity limit of special relativity. Special relativity turned out to be the flat spacetime limit of general relativity. Classical electrodynamics turned out to be the classical limit of quantum electrodynamics. Each of these transitions involved a revelation that the previous framework, while accurate within its domain of applicability, was missing something fundamental that became apparent only when the domain was extended. The standard model of cosmology has worked beautifully within the domain of observations it was constructed to explain. Webb is extending the domain. It is showing us regions of the universe and epochs of cosmic history that previous instruments could not access. And in those new regions, the standard model is showing signs of strain. This is exactly the kind of moment when a deeper framework might emerge. The honest answer about what is going on at the edge of the universe is that we do not yet know. The data is real, the galaxies are there, the anomalies are confirmed, but the explanation is still being worked out. And the work is happening at high speed. New papers are appearing every few weeks, new data is being released every few months. New theoretical proposals are being made and tested against the observations in real time. The pace of discovery in cosmology has not been this rapid since the late 1990s, when dark energy was first detected and the standard model began to take its modern form. We are likely in another moment of comparable significance now. What we learn over the next decade may rewrite the textbooks. While the theorists work on possible explanations, the observers are pushing Webb and its companion instruments to their limits to gather more data. The James Webb Space Telescope is not the only tool in this effort. The Atacama Large Millimeter Array, a radio telescope in Chile, is being used to study the cold gas content of high redshift galaxies, providing information about the raw material from which stars form. The Hubble Space Telescope, despite being older than Webb, is still operating and contributing observations at wavelengths Webb cannot access. Ground-based telescopes around the world are being used to confirm Webb's findings and to extend them, and the next generation of instruments is on the way. The Nancy Grace Roman Space Telescope, scheduled for launch later this decade, will have a field of view roughly 100 times larger than Webb, allowing it to survey enormous patches of sky for high redshift galaxies. The European Space Agency's Euclid mission, already operating, is mapping the distribution of galaxies and dark matter across enormous volumes of the universe. The Vera Rubin Observatory, a ground-based telescope in Chile, is beginning a 10-year survey that will repeatedly image the entire southern sky, producing a dataset of unprecedented size. Together, these instruments will provide a comprehensive view of how galaxies form and evolve across cosmic time. And every one of them is sensitive to the kind of anomalies Webb has been uncovering. There is one particular observation that I want to dwell on because it captures the strangeness of what Webb has revealed. Among the galaxies Webb has detected at high red shifts is a small population of objects that appear extremely red. By red, I mean their light is concentrated at long wavelengths, even after accounting for the cosmological redshift that stretches all light from distant objects. These objects are sometimes called little red dots in the literature, and they have been a source of intense interest since they were first identified in Webb data. The little red dots are unusually compact, unusually red, and unusually numerous. The standard interpretation is that they are very dusty galaxies, with their starlight reddened by the dust they contain. But the amount of dust required is difficult to explain at those early epochs. An alternative interpretation is that they are active galactic nuclei, the central regions of galaxies powered by feeding supermassive black holes, and that their red colors come from the spectral characteristics of the accretion disks. If this is correct, then the little red dots represent a previously unrecognized population of feeding supermassive black holes in the early universe. The implications would be enormous. It would mean that supermassive black holes were more abundant in the early universe than we thought. It would mean that the seeds of those black holes formed even earlier than current models predict. It would mean that the cosmic history of black hole formation and growth needs to be substantially revised. The little red dots have been confirmed by multiple independent analyses. They are real. They are numerous. They are challenging our understanding of what was happening at the edge of the universe. Another remarkable Webb discovery concerns the distribution of galaxies on the sky at the highest redshifts. The galaxies are not randomly distributed. They cluster in patterns that suggest the cosmic web of large-scale structure was already forming in the first few 100 million years after the Big Bang. This is a surprise. The cosmic web is supposed to be the product of billions of years of gravitational evolution, with matter slowly flowing from underdense regions into the filaments and nodes where galaxies cluster. To see hints of the cosmic web already taking shape at redshifts above 10 implies that the gravitational evolution was much further along than we expected. The web was already weaving itself. The threads were already in place. The filaments were already developing. And this provides another constraint on theories of cosmic structure formation. Whatever physical mechanism explains the bright galaxies and the early supermassive black holes must also explain why the largest scale structures were forming so early. When you put all of these pieces together, what emerges is a picture of an early universe that was, in many ways, far more cosmologically advanced than the standard model predicted. The structures, the chemistry, the radiation, the large-scale patterns, all of them point toward a universe in which the seeds of complexity were laid down very rapidly and in which subsequent evolution proceeded at speeds that we did not anticipate. The reason this matters is that it has implications for everything that came after. If the early universe was richer than we thought, then the modern universe is the product of a different history than we have been telling. Some of the things we have been confident about, the age of the oldest stars, the timing of the first galaxy mergers, the formation history of the cosmic web, may need to be revised. Some of the things we have been confused about, the early appearance of supermassive black holes, the chemical enrichment of the intergalactic medium, the patchiness of reionization, may turn out to be consequences of an early universe that was simply more active than we modeled. The new picture is not yet complete. We do not yet know how to assemble all of the Webb findings into a single coherent narrative. But the assembly is happening. The pieces are being fitted together. And the picture that is emerging is one in which the universe accomplished its early structural work with remarkable speed, leaving us with a cosmos that is older in its development than its actual age would suggest. This raises a question that has been haunting cosmology for decades, and that the Webb findings make more pressing. The question is whether our concept of the age of the universe is even quite right. The standard answer to how old the universe is comes from the cosmic microwave background and the lambda CDM model. The combination of these gives an age of 13.8 billion years with an uncertainty of about 30 million years. This age has been confirmed by independent methods, including the dating of the oldest globular clusters in the Milky Way and the analysis of the white dwarf population in our galaxy. Both of these independent methods give ages that are consistent with the cosmic microwave background-derived age. But if lambda's CDM has problems, if some of its assumptions are wrong, then the age of the universe derived from it might also be slightly wrong. The Webb findings suggest that the universe may have done more in its first few 100 million years than the model predicts. If that is the case, the age could be modestly underestimated, or the rate at which structures formed could be different from what the model assumes, which would affect the interpretation of the data. Or there could be some combination of effects that we are not yet able to disentangle. Most cosmologists today still accept 13.8 billion years as the most likely age, but the level of confidence in that number is becoming less absolute than it was a few years ago. The crisis in cosmology is, among other things, a crisis of confidence in some of the most basic numbers that define the universe. There is one more thread I want to pull on before we move further into the implications of what Webb has shown us. It concerns the relationship between dark matter and ordinary matter, and how that relationship played out in the early universe. In the standard picture, dark matter and ordinary matter are intimately related but fundamentally different. Dark matter does not interact with light. Ordinary matter does. Dark matter collapses first under gravity. Ordinary matter falls into the gravitational wells dark matter creates. The two components are believed to have the same large-scale distribution because they share the same initial fluctuation spectrum from inflation. But on smaller scales, they can behave quite differently. Dark matter forms smooth halos. Ordinary matter, because it can radiate and lose energy, can collapse to much smaller scales, forming galaxies and stars within the dark matter halos. This dance between dark matter and ordinary matter is the basic choreography of cosmic structure formation. The Webb findings suggest that the choreography may have been more elaborate than we thought, especially in the first few 100 million years. The galaxies Webb is finding contain enormous concentrations of ordinary matter relative to what current simulations produce. Either the gas was falling into halos faster than expected, or the gas was converting into stars more efficiently than expected, or the halos were starting from larger seeds than expected. All three of these possibilities have implications for the underlying physics of dark matter and ordinary matter and their interaction. Some theorists have begun to explore models in which dark matter and ordinary matter were not perfectly decoupled in the early universe. In the standard picture, after the era of nucleosynthesis when the first nuclei formed, dark matter and ordinary matter interact only through gravity. They do not exchange energy or momentum through any other process. But what if they did, even a little bit? What if there is a small interaction between dark matter and ordinary matter that becomes relevant under the dense, hot conditions of the early universe but is negligible in the modern universe? Such an interaction could change the rate at which structure forms. It could affect the timing of galaxy formation. It could leave subtle signatures in the cosmic microwave background and the distribution of galaxies. The search for these signatures is ongoing. So far, no clear evidence has been found. But the Webb data is one more place to look. Any model that predicts faster galaxy formation in the early universe needs to be consistent with the constraints from later observations, and dark matter-ordinary matter interactions could potentially provide the right combination of effects. While we are on the subject of interactions, there is another idea worth mentioning. The universe contains not only dark matter and dark energy, but also a small fraction of ordinary matter, about 5% of the total energy budget. That ordinary matter is what makes up everything we can see, every star, every planet, every atom in our bodies. The ratio of dark matter to ordinary matter is roughly 6:1. This ratio is one of the fundamental parameters of the standard model of cosmology, and it has been measured to high precision through the cosmic microwave background and other observations. But why is it 6:1? What determined that ratio? The standard model takes the ratio as given without explaining it. There are deeper theories in particle physics that attempt to explain the ratio as a consequence of some more fundamental symmetry or process. None of those theories have been confirmed. The ratio remains one of the unsolved problems in cosmology, and it is the kind of problem that may turn out to be connected to the Webb findings. If the early universe was producing more ordinary matter relative to dark matter in the regions where galaxies were forming, or if the conversion of dark matter halos into galaxies was more efficient than expected, that would have implications for our understanding of the underlying ratio and its origins. The picture I am painting is one of cosmological mystery deepening rather than resolving. Every Webb release seems to add a new layer of complexity. Every theoretical proposal seems to address one anomaly while creating tension with another. The simple confident cosmology of a decade ago has been replaced by something messier, more provisional, more alive. And I think this is genuinely exciting, even if it is also unsettling. Science is most interesting when it is at the edge of its understanding, when the data is forcing the theories to evolve, when researchers are arguing about what the next breakthrough will look like. Cosmology is in that state now, and the James Webb Space Telescope is the instrument that has brought us here. But I want to step back for a moment and consider what all of this means at a more contemplative level. The light from MOMZ-14 has been traveling for 13.5 billion years. When it left its source, the Earth did not exist, the Sun did not exist. The Milky Way as we know it had not yet formed. Most of the heavy elements that would eventually make up our planet and our bodies had not yet been forged in stars. The history of life had not begun. The history of life's ancestors had not begun. The history of the chemistry that would eventually give rise to those ancestors had not begun. And yet that light traveled through the expanding cosmos for those 13.5 billion years, crossing through the formation of galaxies and the births and deaths of countless stars, threading its way through the cosmic web, eventually arriving at our solar system, passing through the void between the planets, striking the gold-coated mirrors of a telescope that was launched on Christmas Day in 2021. Light is captured. The information it carries is decoded. The wavelengths are analyzed. The red shift is measured. And we, beings made of atoms that did not exist when that light was emitted, look at the data and try to understand what it tells us about the universe at its beginning. There is something deeply moving about this. The fact that we exist at all is improbable. The fact that we have built the instruments to see the universe as it was a few 100 million years after the Big Bang is more improbable still. The fact that we have the conceptual frameworks to make sense of what we see, to recognize when those frameworks are insufficient, to revise them in response to new data, is more improbable still. We are, in a very real sense, the universe looking at itself. And what we are seeing is forcing us to reconsider some of our deepest assumptions about what the universe is and how it works. The age of the universe, the standard 13.8 billion years, is a number that is easy to state but hard to feel. To make it concrete, consider that the entire history of life on Earth, from the first single-celled organisms to the present moment, spans about 3.8 billion years. That is more than a quarter of the age of the universe. Our solar system formed about 4.6 billion years ago, which means the solar system has existed for about a third of the age of the universe. Modern humans appeared roughly 300,000 years ago, which is about 0.002% of the age of the universe. Civilization, agriculture, written language, all of these are recent developments on cosmic timescales. From this perspective, the universe has been quietly assembling itself for an extraordinarily long time. The galaxies, the stars, the planets, the chemistry, the biology, all of it has accumulated over 13.5 billion years of cosmic evolution. And the light that Webb is now capturing is the earliest light we have ever managed to detect. It is older than the Earth by a factor of 3. It is older than the universe's first stable nuclei by a factor of millions. It is the closest we have ever come to seeing the universe in its actual infancy. And when we look at that infancy, what we see is something that does not match our expectations. The universe was not the quiet, slowly developing place our models predicted. It was active. It was productive. It was full of structures and processes that should not have had time to develop. The very edge of what we can see is showing us a universe that was already running, already complex, already generating the seeds of everything that would come after, with an efficiency and a speed that we do not yet understand. The mystery is not at the center of the cosmos. The mystery is at the boundary, at the edge, at the moment when the universe was still figuring out how to be. And what Webb is telling us is that whatever the universe was doing in those first few 100 million years, it was doing it with a vigor that our theories did not anticipate. I want to dwell on one more aspect of this before we move into the broader implications. The light from MOMZ14 reached Webb in 2024. The data was analyzed throughout 2025. The paper confirming the redshift was published in January of 2026. That timeline, from photon arrival to scientific announcement, took less than 2 years. By the standards of major cosmological discoveries, that is fast. But consider the longer timeline. The photons themselves took 13.5 billion years to travel from MOMZ14 to Webb. The instrument that captured them required 25 years of development. The theoretical framework against which the discovery is being assessed has been built over a century, going back to Einstein's general relativity and the first measurements of cosmic expansion in the 1920s. The entire infrastructure of modern cosmology, the telescopes, the computers, the software, the trained scientists, the conferences, the journals, has been assembled over generations, and it has all been pointed at this moment, at the edge of the universe, at the question of how everything began. The fact that we can do this at all is one of the most remarkable achievements of our species. The fact that what we are finding is challenging our most fundamental assumptions is, perhaps, the most fitting reward for that achievement. The universe is not the simple machine we hoped it was. It is something stranger, deeper, and more surprising. And every time we extend our reach, every time we look a little farther, every time we measure with a little more precision, we discover that we have only begun to understand it. So where do we go from here? What do we do with the impossible galaxies, the early black holes, the elevated chemistry, the cosmic structures that should not yet exist, the Hubble tension, the hints of evolving dark energy, the cracks in the standard model? The answer, the only answer science has ever had to questions like these, is that we keep looking, we keep observing, we keep building better instruments, we keep developing better theories, and we keep asking what we are missing. Because the edge of the universe is not really the edge of the universe. It is the edge of our understanding, and every time we push that edge a little further outward, we get a glimpse of what lies beyond. What lies beyond, in this case, is a new framework for cosmology, one that can accommodate the Webb findings, one that explains the impossible galaxies, one that resolves the Hubble tension, one that tells us what dark matter and dark energy actually are. We do not yet have that framework. We are still in the early stages of building it. But the foundation is being laid in real time, in the data from Webb, in the analyses being published in the journals, in the conversations happening at conferences, in the equations being scribbled on whiteboards in physics departments around the world. The new cosmology is being born. And it will be very different from the cosmology that has dominated the last quarter century. What that new cosmology will look like is something we cannot yet say with certainty, but there are clues in the data, and there are constraints that any successful framework will have to satisfy. It will need to explain why galaxies were able to form so quickly and so brightly in the first few 100 million years after the Big Bang. It will need to account for the presence of supermassive black holes at epochs when, according to current models, they should not yet exist. It will need to reconcile the two different measurements of the Hubble constant, the early universe value of about 67 and the local universe value of about 73. It will need to make sense of the cosmic microwave background anomalies, the patches of slightly unexpected temperature, the alignments that should not be there, the cold spot that has been puzzling cosmologists for years. It will need to address whether dark energy is truly constant, or whether it evolves over cosmic time. It will need to incorporate the role of dark matter in early structure formation in a way that produces the kinds of galaxies Webb is finding. And it will need to do all of this while preserving the successes of lambda CDM in the regimes where the standard model has worked beautifully. That is a tall order. But the history of physics suggests that when enough anomalies accumulate, a deeper framework eventually emerges that incorporates them all. We have been here before. We were here in the late 19th century, when classical physics could not explain blackbody radiation, or the photoelectric effect, or the stability of atoms. We were here in the early 20th century, when general relativity revealed that gravity was not a force but a curvature of space-time. We were here in the late 20th century when dark matter and dark energy forced us to recognize that 95% of the universe is made of substances we do not understand. Each of these moments led to a deeper, more comprehensive theory of how the universe works. The current moment may be the prelude to another such transition. And the James Webb Space Telescope, by extending our reach into the deep cosmic past, may be the instrument that triggers it. There is something almost poetic about the idea that the most powerful telescope ever built is being used to dismantle the picture of the universe it was supposed to confirm. Webb was not designed to revolutionize cosmology. It was designed to refine our understanding of how galaxies formed. It was designed to fill in details, to verify predictions, to provide the next generation of high-precision data within an established framework. But the universe, when interrogated with sufficient precision, has a habit of refusing to cooperate with our expectations. The data does not always confirm the theory. Sometimes the data overturns the theory. And when that happens, science is forced to grow. The growth is uncomfortable. It involves discarding ideas that researchers have invested their careers in. It involves accepting that our confident understanding was incomplete. It involves the humility of acknowledging that we know less than we thought we did. But the growth is also exhilarating. It means there is more to discover, It means that the universe is richer and stranger than our model suggested. It means that the work of cosmology is not finished. We are not just polishing the final touches on a complete picture. We are still drawing the picture itself. And the brush we are drawing with is showing us colors we did not know existed. Consider what it would mean if some of the more radical proposals being floated turn out to be correct. If dark energy is not constant, but evolves over cosmic time, the future of the universe is different from what we have been predicting. The accelerating expansion may not continue forever in the way we have imagined. The ultimate fate of the cosmos, whether it ends in heat death or in some other configuration, may depend on the specific evolution of dark energy in ways we have not yet calculated. If dark matter has properties we have not yet identified, the entire history of structure formation needs to be rewritten. Galaxies, galaxy clusters, the cosmic web, all of these would have formed differently in detail, even if the broad outlines remained the same. If inflation produced fluctuations that were not perfectly Gaussian, then the universe carries the fingerprint of physics that operated at energy scales far beyond anything we can reproduce in laboratories. We would have, in the structure of galaxies and the patterns of the cosmic microwave background, a window into physical regimes that are otherwise inaccessible to us. If primordial black holes constitute a significant fraction of dark matter, then the universe contains a population of objects we have only barely begun to characterize, and the history of black hole formation goes back much further than we thought. Each of these possibilities, if confirmed, would change not just one aspect of cosmology but the entire picture. They would force us to rewrite textbooks. They would generate new fields of research. They would open new frontiers for observation and theory. And there is still the deeper possibility, the one that lurks behind all of the others, the one that some cosmologists discuss only in private. The possibility that the universe is fundamentally different from our concept of it in ways we have not yet imagined. Not that the parameters of the standard model are slightly off, but that the standard model is built on assumptions that are not quite true. That space and time are not what we think they are at the deepest level. That gravity is not what we think it is at the largest scales. That the universe contains structures, phases, and dynamics that our current theoretical vocabulary cannot describe. The history of physics has examples of such revelations. When quantum mechanics emerged in the early 20th century, it did not just refine classical mechanics. It revealed that classical mechanics was a special case of a much stranger theory in which particles do not have definite positions until they are measured, in which observation affects the system being observed, in which the universe at small scales operates according to rules that have no analog in everyday experience. The current crisis in cosmology may not be that profound. It may be resolved by relatively modest extensions of the existing framework. Or it may be the beginning of something far deeper, a revelation that the universe at cosmic scales operates according to principles we have not yet glimpsed. We do not know which it will be. But we are looking, and we are seeing things, and what we are seeing is making us think. This is what makes our moment in cosmological history so remarkable. We exist at a time when the universe is observable in extraordinary detail, when our instruments can detect the faint glow of objects from the first few 100 million years after the Big Bang, when our theoretical frameworks are sophisticated enough to recognize when our predictions fail, when our communication systems allow discoveries to be shared globally in days rather than decades. We are positioned to participate in a major scientific transition. Not all generations have that opportunity. Most generations live and die within an established framework of understanding, contributing to the refinement of that framework but not witnessing its replacement. We may be different. We may live in a generation that sees the foundations of cosmology reformulated. The children being born now may grow up in a world where the cosmology they learn in school is fundamentally different from the cosmology their parents learned. And that change will have been catalyzed in part by the discoveries Webb has been making at the edge of the universe. I want to return one more time to MOMZ14, the galaxy that started this story. There is something about this specific object that captures the larger mystery. The galaxy is small, just 240 light-years across. It is compact, more compact than any galaxy in our local universe of comparable luminosity. It is bright, producing as much ultraviolet light as galaxies thousands of times its size. It is chemically enriched, containing elements that should not yet have been produced. It has cleared the cosmic fog in its immediate vicinity, ionizing the surrounding hydrogen at an epoch when reionization was supposed to be only just beginning. It is, in every way that matters, ahead of schedule. And it sits at the edge of what we can see, the most distant confirmed galaxy in the universe, looking back at us across 13.5 billion years of expanding space. When we look at MOMZ14, we are looking at the universe as it was when it was less than 2% of its current age. And what we see is not a fragile, struggling, half-formed thing. We see something that is already vigorous, already developed, already doing things that should not be possible. The edge of the universe, as Webb is revealing it, is not the gentle pre-dawn of cosmic history we expected. It is something more dramatic, more advanced, more puzzling. It is a universe that was already up and running, already producing the kind of structure that takes billions of years to make, in a fraction of the time the standard model allows. And beyond MOMZ14, there are surely other objects waiting to be discovered. Webb has surveyed only a small fraction of the sky. The next generation of instruments will survey more. The patterns we are seeing at the edge of the universe, the bright galaxies, the early black holes, the unexpected dust and chemistry, are likely to be even more pronounced as we observe more of the early universe. The crisis in cosmology will deepen before it resolves. The pressure on the standard model will increase. And eventually, perhaps within the next decade, perhaps within the next 2 decades, a new framework will emerge that makes sense of all of this. It will incorporate the insights of lambda CDM where they are correct. It will extend the model into the regimes where it has failed. It will explain the impossible galaxies, the early black holes, the Hubble tension, the evolving dark energy hints, the cosmic microwave background anomalies. It will tell us what dark matter is, or it will replace the concept of dark matter with something more accurate. It will tell us what dark energy is, or it will replace the concept of dark energy with something more accurate. And it will paint a new picture of how everything began, how the universe assembled itself, how the cosmos we inhabit came to be. But it will not, in all likelihood, answer every question. Each major transition in physics has solved old problems and introduced new ones. Quantum mechanics resolved the puzzles of atomic structure and blackbody radiation, but it introduced the measurement problem and the deep mysteries of quantum entanglement, which remain debated more than a century after the theory was first formulated. General relativity resolved the puzzles of gravity and explained the precession of Mercury and the bending of light, but it predicted singularities and black holes that we are still grappling with. The new cosmology, whatever it turns out to be, will likely resolve the current crisis but open new ones. It will tell us things we did not know. It will leave us with questions we have not yet thought to ask. That is the nature of science. It does not converge on a final understanding. It progresses through a series of provisional frameworks, each better than the last, none ever complete. And we live our lives within whatever framework happens to be current. We learn the cosmology of our time, we marvel at the universe through its lens, and we hand our understanding to the next generation, who will improve it. There is a particular kind of intellectual humility that comes from this perspective. The cosmologists who built lambda CDM in the 1990s and 2000s were brilliant. They worked with what they had and produced a model that successfully described the universe with extraordinary precision. Their model is not wrong exactly. It is incomplete. It worked beautifully within the domain of observation it was designed for, and it is now showing its limits as new observations push beyond that domain. The same will be true of whatever framework comes next. It will work beautifully within its domain, and eventually some future generation of observations will push beyond that domain, and another transition will begin. This is not a story of failure. It is a story of the gradual, persistent, sometimes painful enlargement of human understanding. Every generation contributes. Every generation also has to be ready to be surprised. Every generation has to accept that the picture they hold of the universe will, in some respects, turn out to be incomplete. When you stand outside on a clear night and look up at the stars, you are participating in something very old. Humans have been looking at the night sky for as long as humans have existed. The stars you see are the same stars our ancestors saw, more or less. The patterns of constellations were named thousands of years ago. The wonder is ancient. But the framework you bring to that wonder, the understanding of what stars are, of how far away they are, of what they are made of how they were born and how they will die, is entirely modern. None of that understanding existed 500 years ago. Most of it did not exist 100 years ago. And the picture you carry of the largest scales, of the universe itself, of how it began, and how it evolves and where it is going, is changing as you stand there. The James Webb Space Telescope is changing it. The Hubble tension is changing it. The cosmic microwave background measurements are changing it. The next generation of instruments will change it further. The wonder is constant. The framework around the wonder is always being remade. So what should you take away from the discovery of MOMZ-14 and from the broader crisis Webb has helped to trigger? A few things, I think. The first is that the universe is more remarkable than our models prepared us for. We thought we had a good handle on how galaxies formed. We were wrong. Or at least incomplete. The universe in its infancy was doing things we did not expect. That is humbling. And it is also thrilling. It means there is more to discover. The second is that science works. The reason we know that our models are incomplete is because we built instruments precise enough to detect their failures. We continued to test our theories against the data, and when the data did not match the theories, we did not pretend it did. We are now working to improve our understanding. That is what science is supposed to do. The third is that our place in the universe is even more precarious and precious than we knew. We exist at a particular moment in cosmic history, surrounded by structures that took billions of years to form, looking back at a universe that operated according to rules we are only beginning to understand. The fact that we are here at all, that we have built the instruments to see the edge of the universe, that we have the conceptual capacity to grapple with what those instruments are revealing, is a kind of miracle. It is not a miracle in the religious sense. It is a miracle in the sense of being so improbable that its actual occurrence demands appreciation. The light from MOMZ-14 traveled for 13.5 billion years to reach us. It crossed an expanding universe. It passed through the Dark Ages, through the epoch of reionization, through the formation of the first galaxies, through the birth and death of countless stars, through the assembly of the cosmic web. It arrived at a small rocky planet, orbiting an unremarkable star, where a species made of stardust had constructed an instrument capable of detecting its arrival. The instrument captured the photons. The data was transmitted to the ground. The analysis was performed. The conclusions were drawn. And those conclusions are telling us that the universe is not what we thought it was, that the standard model is incomplete, that the early cosmos was already doing things we cannot yet explain. There is, in this chain of events, a kind of magnificent absurdity. The universe is so large, so old, so strange, and yet it has produced beings that can study it, that can see its earliest light, that can recognize the limits of their own understanding and work to extend them. We are, against all odds, here. And we are looking. What James Webb has found at the edge of the universe is, ultimately, a mirror. It is showing us something about the cosmos, yes. The bright galaxies, the early black holes, the unexpected complexity at the beginning of time. But it is also showing us something about ourselves, about the limits of our current understanding, about the depth of the questions we are capable of asking, about the persistence with which we extend our instruments, our theories, our minds, toward whatever lies beyond the boundary of what we know. The edge of the universe, in this sense, is always moving. Each generation pushes it further. Each generation discovers new things on the other side of the boundary their predecessors thought was final. And each generation hands the work to the next, with the universe still larger, still stranger, still more inexplicable than the framework they have built to understand it. The mystery of MOMZ-14 and of the impossible galaxies and of the Hubble tension and of the evolving dark energy hints will not be resolved overnight. It may take a decade. It may take longer. The new framework that emerges, when it emerges, will incorporate insights from observations we have not yet made, from instruments that have not yet been built, from theoretical advances that have not yet been conceived. But the work has begun. The data is being collected. The analyses are being performed. The papers are being written. The conversations are happening. And the universe, the actual physical universe out there, is patiently waiting to be understood, indifferent to our progress, generous with its mysteries, larger than anything we can model. We will keep looking. We will keep building better instruments. We will keep revising our theories. And eventually, we will know more than we know now. Some of what we know now will turn out to be wrong. Some of it will turn out to be only part of a larger truth. All of it will be eventually incorporated into a more complete picture. That is what science does. That is what we do. That is what it means to be human in a universe that we are only beginning to understand. Looking up at the night sky tonight, knowing what we now know, I find myself thinking about the photons still arriving. Right now, as you listen to this, photons from MOMZ-14 are striking the mirrors of the James Webb Space Telescope. Photons from other distant galaxies are also arriving, some confirmed, many still uncatalogued, waiting to be detected and analyzed. Photons from the cosmic microwave background are reaching every square inch of our solar system, filling space with the faint glow of the early universe. Photons are arriving from objects we have not yet identified, from epochs we have not yet probed, from regions of the cosmos we have not yet mapped. The universe is sending us information continuously, every second of every day, across every wavelength of the electromagnetic spectrum. And we are catching only a tiny fraction of it. The rest passes through us, around us, beyond us, carrying messages we have not yet learned to read. There is so much more to discover. There are so many more questions to ask. The edge of the universe is not really an edge. It is a horizon, and horizons can be approached, but they cannot be reached. They recede as we advance. They expand as we look. They contain, always, more than we have yet seen. That is the gift the James Webb Space Telescope has given us. Not just images of distant galaxies, beautiful as those images are. Not just data about the early universe, valuable as that data is. The gift is the renewal of wonder, the reminder that we do not yet understand the cosmos, that the universe still has surprises waiting for us, that the work of comprehension is not finished. We are still at the beginning, we are still figuring out what the universe is. And every time we look more carefully, every time we push our instruments a little further, every time we ask a slightly sharper question, we get a glimpse of how much there is left to learn. The universe is vast, it is old, it is strange, and it is more inexplicable than we have any right to expect. And we, the small fragile beings on a small fragile planet, are looking at it, asking what it is, asking how it began, asking what it means. If you enjoyed this exploration of the deep cosmos and what we are learning from the edge of the universe, please like this video and subscribe to Hidden Beyond Stars. Your support helps us keep building these long-form journeys into the biggest questions science has ever asked. Tell me in the comments what you think Webb will discover next. Do you believe the standard model of cosmology is about to be overturned? Or do you think the anomalies will eventually be explained within the existing framework? And what should we investigate together in the next video? These are not just questions for cosmologists, they are questions for all of us. Because we are all participants in the human project of understanding the universe. The light is still arriving, the mysteries are still waiting, and the next discovery may come from anywhere, from a deep field observation, from a theoretical insight, from a measurement that nobody expected to be important. Until then, keep looking up, keep wondering, keep asking. And I will see you in the next investigation here at Hidden Beyond Stars.